All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Still good? Still good for an hour and a half, ago. All right, so today we're gonna just do more direct stiffness stuff today. So I think we stopped right in the middle of an example last time. So I did want to finish that up, just make a couple more points about trusses, and then we'll move on to our final big topic in direct stiffness, which is beams. Okay. And so beams are just kind of another type of element within the direct stiffness system. And so its deformation is going to be different. Okay. And so we'll go over that. We'll go over its element stiffness matrix. We'll do some example problems. And so, you guys kind of know the drill at this point. And then after we're done with beams, so I think we'll probably finish with beams by the end of next week, or hopefully before the end of next week. Then we'll get back to answer stuff after that. Okay. All right, and so remember the project is due next Wednesday, so less than a week from now. I've gotten a lot more questions over the last week about the project, so that's good. And so if you're running into issues with ANSYS or you're getting errors that you don't really understand, let me know, and then I can help you through that, because it is getting close, and so you guys definitely you should at least, hopefully at this point you've already picked your geometry. You've already tried running some simulations, and then you're starting to kind of write the report. And so remember, the report is the one that's going to take a bit more time this time. The simulations, granted, if you don't run into any big errors, shouldn't take too long. It's the report that you want to make sure that you set aside enough time for. Okay. All right. Any questions about anything before we get started for today? Okay, all right. So let's. I'm just going to scroll up here, and all this should be in your notes already. So if it's you don't have to write it down again. Okay. And so last time we were talking about this particular structure right here. So it's a two-element truss here. We have kind of a slanted element and a horizontal element. Okay. The angle that's shown there is about 30 degrees, and we want to solve for the solution of this truss. And I just realized I forgot to give you something, which is the mode. And so the mode is here, which is 25,000 pounds. Okay. So we have a downward load on node 1 in the amount of 25,000 pounds. Okay. And so what we started with last time is we started making the element stiffness matrices. Okay. And the main point that I wanted to kind of drive home here is that when you have elements here that are angled, you want to make sure that you apply the correct theta, or the correct angle, into your calculation. Okay? And so we talked last time about how to actually compute those. So if you start from a lower numbered node, okay, and you kind of start with a line that kind of is parallel with the positive x-axis, the angle that you're going to put in is the amount of rotation that you would do to get to the final configuration. Okay. And so for element A here, the angle that we need is 150 degrees, okay? And then we computed our element stiffness matrix as such. And then for element B, the angle that we're actually working with is 180 degrees. And so, if you look at element B here, the lower numbered node is on the right. And so, we're going to rotate until that is on the left, okay? And so that is 180 degrees. Okay. So now that we have our, element stiffness matrices, let's go ahead and move on to the next step, which is assembly. Okay. And so with assembly, remember, we want to basically assemble these all into one kind of unified framework. Okay. Because ultimately we want to solve this matrix system in MATLAB. And so for a 3-node system here, we have a little bit of an easier time than last time. So we're going to have a 3x3 system, or excuse me, a 6x6. Okay, so because each node is going to have an x and y deformation. So that's going to be d1x, d1y, d2x, d2y, d3x, d3y. So I need to kind of extend this a little bit. Okay. Okay, let me go ahead and label the columns here. So we have d1x, d1y, d2x, d2y, d3x, d3y. Okay. And this is all equal to f1x, f1y, f2x, f2y, f3x, F3Y. Okay. So that's our system, and it always takes like a minute or two just to set it up, just because there's a lot of writing, and probably if you're working on line paper, you probably have a little bit of an easier time because you can get everything to actually line up. So you can see for me, when I don't have lines, it makes it a little bit more difficult. Okay, and so just like before, we're going to basically, we're going to start by boxing out the areas, and so let's go with element A. Okay. Let's check our element A to see what nodes it's connected to. So element A is connected to nodes 1 and 2. Okay. And so nodes 1 and 2 are going to be these areas right here. Okay. So we got kind of one contiguous kind of 4x4 block. Okay. Element B. Element B here is going to be nodes 1 and 3. Okay. Okay, so if we do that, we box off those areas of the global stiffness system. Okay. We have this right here. Okay. All right, and so just like before, we're going to insert our entries here. This is going to be a little bit more cumbersome just because for our element A, our angle there was 150 degrees. And so, we have a lot of different values within the element stiffness matrix, okay? So just for the sake of time, I was actually planning to finish this example last time. So I'm just going to go ahead and fill in all the entries for you, but just kind of remember our usual kind of pattern here. Whenever we have overlapping entries, we just add their things together. Okay. Okay. So just like in the previous example, just to make our lives a little bit easier, I'm going to factor out a factor of 10 to the fifth. Okay. And then all the other entries are look like the following. So 6.875 minus 1.08 minus 1.08 0.625. Okay. Then we have minus 1.875 1.08 1.08 minus 0.65. Okay. Minus 1.875 1.08 1.875 minus 1.08 1.08 minus 0.625 minus 1.08 and minus 1.08. Okay. So you can see here it becomes a lot more. Oh, sorry, that one in the bottom right there is a positive 0.625. I was looking at the wrong line. Okay. Yes. Okay. And so you can see here with when the angle is not 90 degrees or 0 degrees or 45 degrees, it becomes a little bit more cumbersome to add these numbers. Okay. All right. And so thankfully for element B, it's a lot easier. And so we have a 180 degrees. So this is going to be a minus 5, 0, 0, 0. And then a minus 5, 0, 0, 0. And then a positive 5, 0, 0, 0. And of course, everything else that's not boxed is just going to be 0. All right. All right, so that's our global stiffness system. So it's just our usual kind of fitting things in and plugging numbers in, and just adding anything that overlaps. Okay. All right, any questions? Any questions on this so far? Just to give people just a little bit extra time to write everything down. Okay. All right, so then now that we've inserted everything, the next step is the boundary conditions. Okay. So this is where we're going to have something that's a little bit unique, okay? Because remember, if we kind of scroll back up to the problem, you can see that node 3 is fixed by a roller support, and so it's not going to be the same as a pin support. Okay. Okay, but we'll start with node 2. And so node 2 is kind of the more straightforward one. So node 2 is a pin support. Okay. And so because node 2 is a pin support, that means d2x is equal to d2y equal to 0. Okay. So let's go ahead and knock out the rows for d2x and d2y in our global stiffness system. Okay. So our row for d2x is this one right here, d2y, this one right here. Okay. So you can see I did not do a very good job lining these up, but hopefully you did a better job in your notes. Okay. And so let's go ahead and do our usual replacement. So we're going to replace that row, in this case as a third row, with zeros. Okay. We're going to put a 1 on the main diagonal because we're on the we're doing a Dirichlet or a constraint type boundary condition. Okay. And then we're going to put zeros everywhere else. Okay. So that's the pin support. So that's node 2. So that's we've seen that before, right? Node 3 is being constrained by a roller support, right? And so let me kind of draw a small version of that here, just so we don't have to kind of keep scrolling up and down. Okay. So this here's node 3, and it's being supported by a roller, right? And so if you look at the orientation of that roller, if you kind of see that from there, you can see that roller is allowing deformation in the y direction. Okay. And so that roller is going to prevent any deformation in the x direction, but the y direction deformation is still going to be free. Okay. And so in this particular case, we can say that d3x is still going to be 0 because we have a roller that's preventing any deformation in that direction. Okay. But d3y is still going to be free. Okay. And so what that means is that we are only going to make changes to the d3x row in our matrix. Okay. The d3y row, we're actually just going to leave it completely alone. We're not going to make any changes to that at all. Okay. Okay. And so let's go to the d3x row. And so we're going to do our usual things. We're going to change everything to zeros. Okay. Except for the main diagonal. And so the main diagonal, we're going to put an entry of 1. Okay. And then on the right-hand side, we're going to put a 0. Okay. But for the d3y row, and we're not going to do any, we're just going to leave it as it is. Because the roller basically allows for, perpendicular deformation. Okay. Okay. All right. And so let's go ahead and apply our loads, right? And so our only load in this case is going to be on node 1. And so we have a downward load of 25,000 pounds. Okay. And so for F1Y, we're going to have a minus 25,000. Okay. And then F1X and F3X, or excuse me, F3Y are going to be 0 in this case. Okay. All right, and so that's our system, right? And so we've done all the steps of the direct stiffness method. We've computed our element stiffness matrices. We've assembled them all together. We've applied the boundary conditions, and now we're ready to solve. Okay. All right. Any questions on anything that we've done so far? Okay. All right. So that's good. Okay. Unfortunately, if you did actually try to solve this in MATLAB is going to give you an error, or it may not give you an error, but it may tell you that, the deformation that you compute are infinite, okay? And this is the reason why. And so if you look at the final row in the matrix here, Okay. What you'll see is that we have a row of entirely zeros. And if you look at the corresponding column, right, and so in this case would be the last column in that matrix, right, this is also all zeros. What that means is that, you know, we don't have anything that's constraining or nothing that is stopping, you know, E3. And in fact, you know, we have no stiffness, and what you could say is we have no stiffness in that direction as well. Okay. And so what this means is that this system right now, as it stands, is actually under constraint. Okay? So what that means is that there's not enough constraints in this system here to maintain that current configuration. Okay. And so some of you have actually run into this, actually quite a lot of you at this point. Quite a lot of you have run into this error of ANSYS. And so this is the dreaded solver pivot warning. And so if you get the dreaded solver pivot warning, you know, what that's basically saying is that your system is under constraint. Okay. And that could be due to a lack of fixed supports. That could be due to a lack of your connections not being all tight. And so for whatever reason, you know, your model is under constraint and it's not able to kind of maintain that geometry. Okay. And so if you look at our geometry here, right, it looks kind of strange, right? And so, you know, what we know from pin supports is that even though that they prevent, you know, any kind of translation, X and Y translation, you know, you can still have rotation at that node, right? Whereas this bottom node right here, you know, we're only constraining the X direction, but the Y direction is free. Okay. Even in the absence of any kind of weight, right? And so, you know, we're ignoring the weight of the truss elements themselves, right? If you were to push down on this node right here, right, what would you expect to happen? You would expect this whole thing, right, this whole node 3 to slide downwards, right? And so in other words, you would find a new equilibrium position where, you know, where it's fully constrained. Okay. And so when you run into a situation like this, and then, you know, and it's not that common. And so if you run into a situation like this, then the problem itself was kind of ill posed. What you're going to need to do is that in order to get a solution, you have to kind of artificially constrain the system even more. Okay. Yeah.
I have a question.
Sure.
To be honest, I don't remember, but in the whole situation, from statics, one of the forces is equal to zero, but the other force is not equal to zero. I don't remember which one. Is it dx or dy in the whole?
They're both zero in this case, so we're not applying any forces on that rule.
I know, but it's like in statics, one of them it has a force. So
this
why we don't have the force applied here?
So these forces here, these are all external forces. And so in reality, you know, if you do have a roller support or any support, you know, you're going to have reaction forces there that keep the structure.
Yeah, the reaction.
So so there's a way to compute the reaction force. So so we went over that in a previous lecture. So basically what you would do is after you would solve for the displacement solution, then you would plug that in and multiply that by the global stiffness system before you apply boundary conditions. Yeah. And so go back in the notes. We covered this in a previous class.
Okay.
Mhm. Okay. And so for this particular problem, you have to kind of artificially constrain it to get a solution. So the way to do it is to basically just add a 1 to that diagonal. Right? And so effectively what you're doing is by adding that 1 there, we're turning that roller support into a pin support. And so is this kind of true to the original problem? No, it's not, right? So we're basically changing the problem so that we can get a solution in this configuration, okay? But what this is basically telling us is that in the original configuration of the problem, it's not stable enough or not constrained enough to get a solution within that geometry, okay? And so this is something that you kind of artificially have to do in order to get that solution. Now, the question you might be asking is that is this going to be true every time you get a roller support? No, it's not. And so let me kind of give you another example. Where you can have a roller support and you don't end up with a row of all zeros. Okay. This only really occurred because we had a horizontal element and a roller support, that constrained that movement kind of perpendicular to that element, right? Because remember, truss elements are only designed for extension and compression. Right? And so if we were to kind of move vertically there, that would be actually transverse displacement, which is what we're going to cover with beams in a second. Okay. But if you were to have a geometry that looked like this, okay. And so we have a roller support being supported by two elements like that, right? Where neither element is kind of perpendicular to that roller direction, right? This would be a situation where if you apply a horizontal force here, okay, you'd be able to get a non-trivial solution where you wouldn't have to, artificially constrain the problem, okay? And so it doesn't always happen that you have to artificially constrain a problem with rollers. It's just that this particular configuration with rollers, we have to add an artificial constraint in order to get it to work. Okay, that's not that uncommon with real finite elements too, right? I've some of you have already come and talked to me about kind of applying finite elements to maybe your senior design project or your legacy project, right? We've talked about kind of, running your simulation on kind of a subsystem and then kind of artificially adding kind of fixed supports at different locations of your model. So, this isn't that different from that. Ideally, you wouldn't have to do this. Ideally, you could keep kind of the model in kind of the way that you intended. But sometimes in order to get the simulation to work, in order to get a solution, you kind of have to add artificial constraints. And there's a little bit of an art to it in kind of an ANSYS to add these constraints in a way where it's going to be non-intrusive to your solution. Okay. But we'll certainly talk more about that kind of probably after the Thanksgiving. All right. Any final questions on this before we move on to beam elements? Okay. All right. So that's it for trusses. And so let's go ahead and move on to beams. Okay. So beam elements we've kind of already talked about previously in the course, and so that was kind of the subject of activity 4. And one thing I mentioned during that time is that your beam elements are special, and so they aren't just kind of typical 1D elements. They have some additional properties and additional degrees of freedom that allow us to use them in kind of 3-dimensional contexts. Okay, and so we're going to dive a little bit into that here, and then connect it with direct stiffness. Okay. Okay. And so kind of more explicitly, a beam element is a structural element that is capable of transverse displacement and rotation. And so in some ways, you kind of think of them as the opposite of truss elements, because truss elements are only capable of what I call axial deformation. So either extension and compression. Okay. If we were to draw a beam element, transverse displacement is defined as displacement that's perpendicular to the element itself. Okay. And so we call this node 1 on the left, node 2 on the right. Okay. The transverse displacements would be displacements that are perpendicular to this length. So in this case, it would be the y direction. So we have u1 or d1y, okay, and d2y. Okay. And then the other thing that we're capable to compute with beams is rotations. Okay, and so rotations is nothing more than just kind of a change in orientation, or just how much the beam is actually rotated relative to its kind of default configuration. Okay. And so we define rotations using angles. Okay? So we have theta 1 there and theta 2 there. Okay. And so in contrast, beams, at least for now, we're going to assume that beams are not capable of axial deformation and axial, extension and compression. Okay. Okay. In fact, if we were to bring in axial compression and extension, that would be a frame element, and those are legitimately a nightmare. So we're not going to go there. Okay. And so just like we did for truss elements, let's start with the element stiffness matrix. Okay. And so I'm going to skip the derivation in the notes just because we are a little bit behind, and I want to make sure we finish everything in a timely manner, just so we can get back to the answers. And so I'm going to give you the element stiffness matrix. But if you're curious, this element stiffness matrix is derived using Euler-Bernoulli beam theory. So that derivation is in the notes. Okay. Okay. So the element stiffness matrix. And so you can see for the beam here that we have 4 degrees of freedom, right? So we have both the transverse displacement and the rotation. And so that means our element stiffness matrix is also going to be 4 by 4. So just like a 2D truss. Okay. Okay. So the element stiffness matrix looks like this. And so out in front, we're going to have a factor of EI over L cubed. Okay. And I'll define what those mean in a second. And then inside here, we have a 12, 6L minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, minus 6L, 6L, 2L squared, minus 6L, 4L squared. Okay. So definitely keep this handy in your notes, because it's a lot to memorize otherwise. Okay. All right, and so the degrees of freedom here, we have d1y, theta 1, d2y, theta 2. And all this is equal to fy1, m1, fy2, m2. All right, but the part you need to kind of remember is kind of right here on the left-hand side, okay? All right. So it's a lot of entries, right? So a 4x4 element stiffness matrix means that there's 16 entries that you need to write down. Okay. But if you'll notice, we have one kind of nice thing about this element stiffness matrix, which is true for our 2D truss as well, that this element stiffness matrix is also symmetric. Okay. And so you can use kind of the same trick that we did before. It doesn't save you all that much work, but even just a little bit of extra saved time here is big. So remember, the way that we did these was that we wrote, we kind of built up our element stiffness matrix row by row. And so we'd write the first row, and then we know that because this matrix is symmetric, we can write the entries of the first row into the first column. Okay. Then we do the second row, and then the second row becomes the second column, third row, third column, and then the fourth entry just by itself. Okay. So definitely make use of that. So it kind of seems like an extra step, and so it seems like an extra step on top of just writing this down. But when you're writing dozens and dozens, or I'm not going to make it write dozens and dozens, but when you're writing down kind of a lot of these over and over again, it helps to have something like that just to make sure that everything is aligned properly. Okay. Okay. All right. Any questions? Any questions on this so far? Okay. All right. So before we jump into an example, I do want to kind of revisit the discussion of constraints. Okay? Okay. And so far for the truss elements, we've seen pin supports and we've seen roller supports. Okay. Now that we have a rotational degree of freedom here, we have to kind of talk about how those different constraints will constrain that rotational degree of freedom. Okay. Okay. And so there are three types of constraints that we're going to use here, and I'll actually go from most loose to the most rigid. Okay. Okay, so let's talk about the most loose support first. Let's talk about the roller support. Okay. And so roller support is denoted by kind of it's like a little skate there. Okay. All right. Right. And so in the most kind of flexible case, we have 3 degrees of freedom that we can have at that node. We have a displacement in the x direction, we have a displacement in the y direction, and we have a possible rotation theta 1. Okay. And so for the roller support is only going to constrain the deformation perpendicular to that roller. Okay. And so in this case, we're gonna have d1x. So d1x is not going to be constrained here. So d1x is going to be free. Okay. Right. d1y here is going to be constrained because it's it's a roller, so it's going to prevent any kind of deformations in that direction. Okay. And a roller support also will not allow any will not constrain the rotation. So theta 1 is also going to be free. Okay. And so a roller support is only going to prevent displacement in this case in the y direction. Okay, so that's the roller support. Let's talk about pins. So pins is the one we kind of see most common in trusses. Okay. So a pin typically looks like this, and so it's a support that's a triangle, and that triangle is kind of fixed to the ground. Okay. And so just like before, I'm going to list out our 3 degrees of freedom here. So d1x, d1y, and theta 1. Okay. And so a pin support is going to prevent all translational degrees of freedom. So D1X and D1Y are both going to be equal to 0 in this case. Whereas theta 1, right? A pin support, if you kind of think about it as literally like, you're pinning it to a wall, right? A pin does not, it does not constrain any rotation. So in this case, theta 1 is going to be free. Okay? All right, and then finally we come to kind of the most powerful constraint, which is the fixed support or the fixed constraint, okay? Which is the one we typically use in ANSYS. And so fixed support usually looks like this. And so we usually see it's almost kind of like welded or kind of bolted to a wall, kind of completely like that. Okay. And so a fixed support or a fixed constraint is going to be the most powerful. So it's going to prevent all translation and rotation. So in this case, D1X is going to be 0, D1Y also going to be 0, and theta 1 also going to be 0. Okay. Thanks. Any questions on these before we jump into example? Yes.
To be clear, these conditions would just be on like the left side of the beam where like those are actually at, and the right side is.
Exactly. Right. So these only apply for the node that's going to be where the constraint is. Yeah. Good question. Okay. Let's do a simple example. So this one should be hopefully pretty fast. Although what I'm finding is that my example is going to take longer than I thought. Okay. All right. So let's consider this 2-element beam. And so we're going to have beam A, and then we have beam B. Okay. Right, and so we're going to label all the nodes in our system. We have node 1, node 2, node 3. Okay. All right, so node 1 we're going to say is fixed to a wall. Node 3 we're going to say is pin. Okay. And then for the modes, we're going to have a downward force with the magnitude of P. And at the same time, we're going to apply a torque onto node 2. And so that's going to have a value of M. We have our force P and our torque M applied on node 2. Okay. And so this one, I'm just going to solve symbolically. So we're not going to plug in any numbers here. And so we'll assume that all the properties are given. In fact, we're going to assume that beam 1 and beam 2 have identical properties. And so the same E, same I, and the same L. Okay. And I'm just realizing I didn't define what I was to you, so I'll do that in a second. Okay. Okay. And so for this problem, since we don't have numbers, we can't solve it for a solution. And so let's solve instead for the global stiffness system with the boundary conditions applied. All right, and so to find our global stiffness system, we're going to have to go through our usual direct stiffness method, okay? So let's go ahead and start with the element stiffness matrices. Okay. And so in this case, both of the element stiffness matrices are going to be identical. The only difference being is in terms of the nodes that they act on. Okay. Okay, so let's do element stiffness matrix for element A. Okay. Since we're not given any numbers here, we're just going to do everything symbolically. So we have EI over L cubed. Okay. Let me define I for you here, and so I know it's a little bit out of place, but this I here, okay, this I here refers to the moment of inertia of the beam's cross section. And so depending on the cross-sectional shape of the beam, you can compute its moment of inertia from it. Okay. And so, for this class, I'm not going to make you compute these because I know that there's a whole table of different shapes and things like that. For the most part, if I'm going to ask you to solve a problem with numbers, involving beams, I'm just going to give you the value of I directly. So you just got to plug it in. Okay. Okay. So now that we've defined I, we can go ahead and write out the elements of the element stiffness matrix. And so let's start with the first row. So the first row is 12, 6L, minus 12, 6L. Okay. Let's take that first row and write it into the first column like we usually do. And so this is going to be 6L minus 12, 6L. Okay. All right, second row. So second row is going to be 4L squared minus 6L, 2L squared. We're going to do the same thing, write that into the second column. Third row is 12, and minus 6L, minus 6L, okay? And in the bottom right, we have a 4L squared. All right, and so since element A is connected to nodes 1 and 2, we're going to have a D1Y, theta 1, D2Y, theta 2. Okay. All right, and so for element B here, we're just going to write the exact same thing, except with different nodes. And so I'm just going to do that one really quick. So those are all the entries. And then element B here is going to be connected to nodes 2 and 3. So we have a D2Y, theta 2, D3Y, theta. Okay. So those are our element stiffness matrices. And so, it's pretty straightforward here. So now our next step is assembly. Any questions on this so far? Okay. So let's go ahead and assemble these into a single system. Okay. And so our system here, our global stiffness system is going to be 6 by 6. Okay. Make sure I leave myself enough space. So you have a D1Y, theta 1, D2Y, theta 2, d3y, theta 3. Okay. Let me go ahead and write in the columns here. So we have d1y, theta 1, d2y, theta 2, d3y, theta 3. Okay. And then on the right-hand side, we're going to write in all of the nodal forces. And so we have an F1y, M1, F2y, M2, F3y, M3. Okay. Okay, so let's go ahead and write in the our element stiffness matrices. And so let's start with element A. Okay, so element A is going to be connected to nodes 1 and 2. So let's go ahead and box that entry in our system here. So that looks like the following. Okay. And then element B. Element B here is just going to be nodes 2 and 3. So, nice thing is that we have kind of a nice contiguous block here, just like the other one. Okay. So those are our two element stiffness matrices. So let's go ahead and fill in the values here. Okay. And so I'm going to keep EI over L out in front, just so just so we don't have to kind of write that into the matrix. But don't forget that. And so, I think one of the more common mistakes that I see with people making direct stiffness is that, you work really hard, you get your global stiffness system, you go to solve it, but then you kind of forget that factor out in front. So make sure you don't forget that guy. Okay, so for element A, let's go ahead and add in the entries here. So we have a 12, 6L, minus 12, 6L. Okay. 4L squared minus 6L, 2L squared. Okay. Then down here we have a 12 minus 6L minus 6L and a 4L squared. Okay. So that's just for element A. Okay. All right, so let's do the same thing for element B. So we're going to fill in just the same entries there. Okay. And so we have a plus 12, plus 6L, plus 6L, plus 4L squared. So that takes care of all the overlapping entries. I'm just going to fill in all the other entries really quickly here. Okay. And then of course everything else that's not boxed here, we're just going to put a 0. So we got zeros here and there. All right, so this is looking good. And so now that we have our assembly done, next step is to apply our boundary conditions. All right, so we have quite a few boundary conditions to apply in this case. Okay, let's start with our constraints. And so our constraint is that we have a fixed constraint on node 1 and a pin support or pin constraint on node 3. Okay. Okay. And so let's go ahead and apply these. And so for a fixed constraint on node 1, that means both its translational degree of freedom, which is d1y, and its rotational degree of freedom, theta 1, both of those are going to be 0. So that's going to knock out the first 2 rows of our matrix here. Okay. Okay, so that matrix you work really hard to write down. I'm going to erase half of it. Okay. We're going to put a 1, 0, 0, 0, and then a 0, 1, 0, 0. Okay. And then on the right-hand side, we're going to erase those as well. And so on the right-hand side, we're going to have 0, 0 there. All right, and then the pin support on node 3, that's only going to knock out the translational degree of freedom node 3, and so that means d3y is going to be 0, but theta 3, that one's not going to be that one's going to remain free. So we're gonna leave the last row of the matrix alone, and only the second to last row, that's the one we're going to knock out here. Okay. Okay. Oh, let me knock that right. Okay, so that's what the second to last row in the matrix looks like. We have a 1 on the diagonal entries, which is the second to last column, and then everything else in that row is going to be 0. Okay. All right, and so the last thing we have to do here is just add our loads. And so we have 2 loads here. Okay. Okay. And so we have a downward force P applied on node 2. And we also have a counterclockwise torque M applied on node 2 as well. Okay. And so both of these are being applied on node 2. And so they're going to take the place of F2y as well as theta 2, okay? Or M2. Okay, so let's go ahead and fill those in. Okay. And so for the force that's being acting on node 2, we know it's a downward force, and so we're going to put a minus P there. Okay. And then for the moment that's being applied on node 2, okay, we have a counterclockwise torque. And so when our torques are counterclockwise, then we input it in as a positive number. And so we have a positive M being applied on node 2 as well. Okay, and so the last thing that we have here is node 3. And so the moment on node 3, we don't have any load there. And so we're going to put a 0 on that last row. Okay. All right, and so at this point, if we had numbers, we can go ahead and plug in all the numbers into everything and solve for the solution. But since we don't have numbers, this is kind of as far as we can take it. I guess if you wanted to simplify it, you can simplify this this middle matrix here, okay? Because some of these are going to cancel out here. Okay. And so you would have a 24, 0, 0, and then 8L squared. And so, that's about as far as we can take it though, because because we don't have any numbers. Okay. All right. Any questions on this? All right. Looks good. All right, so I do have one more example today. I don't know if we're going to cover. I know if we're going to get to finish it, but I at least want to start it. But before I do the next example, let me talk a little bit about the rotations again. And so the rotational degrees of freedoms on beams is actually quite unique. Okay. And so let's go back to activity 4 when I mentioned that the beam elements and the shell elements, they kind of have an extra degree of freedom that kind of makes them special in 3 dimensions. Okay. And so that extra degree of freedom that I was talking about back then was these rotational degrees of freedom. And so your typical solid elements, and so your typical tetrahedrons and your hexahedrons, they don't compute any rotational degrees of freedom, because they're 3-dimensional objects, right? And so there's no need to kind of, estimate any kind of rotation, because any rotation or any kind of change in orientation of a 3D object can be just captured by the 3D object itself. Okay. And so, we're not going to use these rotational degrees of freedom for this context here. But what those rotational degrees of freedom allow you to do is that it allows you to compute things like the stresses and the and any kind of strains and deformations without the need for derivatives. Okay. Because normally, remember what we talked about when we talked about shell and beam elements. If you wanted to compute the stress in a solid element, you need to take the derivative of the deformation distribution, right? And if you have a situation where you have only one element through the thickness, so you have a slender element, that can be either very difficult to do, or it's going to give you something inaccurate, right? But since beam elements and by extension shell elements as well, because they compute this rotation, in other words, they kind of directly compute, its change in orientation as a result from any kind of loading, then you can compute things like stresses and strains without taking derivatives. And that's kind of the power of beam and shell elements, is that it allows you to compute stresses a lot more accurately for thin geometry. So, in some sense, you can kind of say that it computes it directly, as opposed to solid elements, which kind of has to derive it from the deformation solution. So, that rotational degree freedom, it is quite special and something that's unique to beams and shells, that kind of set it apart from solid. Okay. And so I know, this is kind of taking us back to a few weeks ago, but I at least wanted to point this out, to kind of give you some additional context in terms of, why shell and beam elements work so well, for those situations. Okay. Okay, so let's do one more example today. So let's start it, and then we'll probably finish it up on Tuesday. Okay. And so similar to the last example, we're gonna have a two element system. Okay. We're gonna have a fixed wall, just like before. Okay. We're gonna have element A, element B. Okay. We're gonna have numbers here, and so we're gonna say that the lengths of these beams are each going to be 3 meters. Okay. Let me label the nodes, and so the nodes are node 1 on the left, node 2 in the middle, and node 3 on the right. Okay. But in this case, I'm going to add an additional element here, but it's not going to be a beam. It's actually going to be a spring. And so we're going to add a spring here, like this. And we're going to assume the spring is going to be fixed to the ground at the bottom. Okay. So we're going to call the spring element, we'll call that element C. Okay. And then this node on the bottom here, we'll call that node 4. Okay. Okay, so let me give you the numerical values for the properties. And so let's say the two beams are identical. And so they're going to have the same Young's modulus and the same moment of inertia. So E here is going to be 210 gigapascal. Okay. The moment of inertia, we're going to say is 2 times 10 to the minus 4 meters to the fourth. Okay. And our spring constant K here is going to be 200 kilonewtons per meter. Okay. Okay. And so what we're going to do is we're going to use the direct stiffness method. We're going to use the direct stiffness method to compute all the nodal displacement and the nodal rotations in the structure. All right. So we have an interesting case here. So this will be kind of the first time we've combined beams and springs. Okay. And so, on the one hand, if you kind of go back to kind of when we first started talking about beams like 30 minutes ago, what I told you was that beams don't deform in the same way, or at least their methods of deformation are not the same, right? And so beams, at least in terms of our calculations, and at least in terms of our element stiffness matrix, the beams are only capable of transverse displacement and rotation. What beams are not capable of is axial displacement, okay? But that's what a spring does. And so a spring is capable of axial deformation. Okay? I bring this up because, when you have, two elements that are kind of put together and their modes and if their degrees of freedom are incompatible, then it will be very difficult to solve, if not impossible. Okay. So for example, let's say that we have a beam. Okay. right? So we know for the beam, we have degrees of freedom that look like this. And so we have a D1y, theta 1, D2y, theta 2, okay? Now let's say that we connect this to a spring that looks like this, okay? Whereas for the spring, you know, we know that we have a D, we'll call this D3x, and a D2x on the left-hand side. Okay. I wrote it down, I swear. It's just the computer, the internet is lagging. Okay. All right, I'm just going to keep talking. All right, and so in this case, you know, we have two elements here that are connected, but they're incompatible, right? And so the deformation, there it is. The deformation modes for the beam kind of go in the y direction in this case, whereas the deformation modes of the spring go in the x direction. Okay, and so when we go to actually solve, or when we go to actually compute, you know, or assemble the global stiffness system around that node, you know, we're going to have entries that are kind of incompatible with each other. Okay, which is, you know, which is not the worst thing. It's just, you know, it's just going to make our system a lot more complicated than it is. Okay. Because if you can imagine at node 2 right there, you know, we're going to actually have 3 degrees of freedom that we're going to solve for. But, you know, it's, you know, which, you know, again, it's not the worst thing, but, you know, at least structurally, you know, we're not going to have any overlapping entries in this case. And so the spring is basically going to act basically almost independently of the beam in this case, because, you know, they're not adding stiffness just because their deformation modes are kind of incompatible. Okay, and so we would be able to solve the system, but it wouldn't really be accurate because, you know, the beam is not really affecting the spring, and the spring is not really affecting the beam because the degrees of freedom are incompatible. Okay. It's more the non-interactivity that's kind of the kicker here, because, you know, if you have two structural elements that are connected together, you would think that the solution of one element or the stiffness of one element is going to affect the solution in the other element as well. But when you have incompatible degrees of freedom, that's not going to happen. You're going to have the two things kind of you know, completely unrelated. Okay, because in all of our other direct stiffness problems, you know, we've had situations where we had parts of our global stiffness matrix overlap with multiple elements, right? And so whenever we have multiple element stiffness matrices overlap, that means that, you know, those two elements are actually interacting with each other, and their solutions are affecting each other, which is what we want in finite elements. Okay, and so a situation like this is not, you know, is not usually not what we're looking for. Usually not good. Okay. But we don't have that situation quite here, right? And so in this example here, the spring is actually perpendicular to the beam itself. Okay. And so the spring, we know, is going to displace in this direction, right? In this case, it's going to, the axial direction is the same as the y direction. Okay? Whereas the beam at this node is also going to be displacing in the y direction as well, right? So it's going to be a transverse displacement going up and down. Right? And so because these two degrees of freedom are the same, or you know, and that they can interact with each other, we have a situation here that's actually okay. Okay? And so because these two degrees of freedom are going to they're basically kind of matching up. Okay, these two elements can actually interact. The only thing that we have to be careful for is that, you know, one way that you can kind of consider this the spring element is that it's a 2D element that's kind of rotated up by 90 degrees. or actually technically because the node is up here, technically it's 270 degrees, okay? And so we want to make sure that, we want to make sure that when we assemble our global stiffness system, they're going to be assembled in a way where those two things are going to overlap, okay? And so that's kind of a good rule of thumb, kind of when you're kind of doing these problems too, that you should, if your problem is decently well posed, you should get a decent degree of overlap when you go to assemble your system. If you don't have any overlap, that means your elements are not interacting with each other at all. Okay. Okay. Any questions on that? Okay. Okay. We have 3 minutes. Let's call it here for today, and so we'll pick up this example on Tuesday, because I think the next step is just writing down the element stiffness matrices, but that would just kind of be filling time because we have to write them again on Tuesday. So let's end a little bit early today, and so on Tuesday we'll pick up this example again. We'll write out their element stiffness matrices. We'll assemble them together, and we'll see how it looks, and then we'll move on to the last topic of direct stiffness, which is distributed loading. Okay. All right. So thank you guys for coming today. We're almost done with the direct stiffness section, and so I think next lecture we should be able to wrap it up. And so after that we'll get back into doing this stuff. So remember, the project is due on Wednesday, and so I have a couple office hours before then. So I have Tuesday morning 9 a.m. That's virtual only, and then Wednesday 5:30 to 6:30. Okay, so you can stop by those office hours if you need any extra help. With regards to the direct stiffness system, I am going to assign a homework. Set regarding this soon, probably tomorrow. And so I'm going to post that, but that's not going to be due until basically right before Thanksgiving for the midterm. Okay. All right. So thank you guys for coming today. Hope you guys enjoy your weekend, and I will see you guys next week. Thanks, you too. Yep. Sure. Yeah. Oh, okay. Yeah. So it is gradually level. It's actually going to be very different. So, what we're talking now is the direct stiffness. This is like, I want to talk like baby formula, right? And so, in reality, what elements, there's kind of a lot more kind of advanced now. So if you're really into that stuff, it's really into the direct stiffness stuff. There'll be a lot more of that. Right. Well, 541 would be a good number. You want to do that for most insurance companies, it's okay to look at it. If they're doing kind of something really unique, yeah, so most cases, 541, if something, so we're not going to need. Actually, the good one is one of the original answers, 540, which I just taught in last. Probably not going to. But the grad course we put on like a 3 semester. Well, thank you. Yeah, I mean, I'm probably next day. Okay. Yeah. You'll need a bunch of other guys. Well, does that count as collected? Yeah. Okay, cool. We would have to fill out a petition, but yeah, it's an advance and report in each area, so it'll be enough. Cool. You might have to fill out a petition. So if it's not going to let you enroll, then just let me know, and then I will fill out a permit. Okay. Thanks. Yeah. You too.